Hello, everyone. Jorge, are you there?
Hi, yes, I'm here.
Hello.
Hello.
Nice to see you, Jorge. Back.
Hello. I have to move my Zoom to the other desktop, or wait a moment. I will up in this desktop the presentation. Google Slides. Because I don't see the other desktop here. There it is.
In any case, we have still 3 to 5 minutes, so the full program for today.
Okay, now I have it here. Okay. Okay, so the first, second is Lian Li, third one you. Okay.
Okay, hello everyone, good morning. I think we shall start the morning session of the last day of the school. And the first speakers of today is Jorge Rueda from ICRANET and INAF. And okay, Jorge, if you want to start to share the slides.
Yeah. Yes, okay. Let's see if it works. Can you see it now?
Yes.
Let's do full screen now. Do you see also the Zoom window here on the right part or not? Or you see only the...
Yes, we see the full screen of your presentation and your
okay, I hide
your image.
I minimize the Zoom now. Okay, it should be okay now. It's okay now?
Yes, it's perfect.
Then you see, okay.
Okay, you can start, Jorge, and you will have 40 minutes.
Okay, thank you, Carlos. First of all, thank you for the for having me here to speak. Let's see. Somehow I will summarize what is the binary-driven hypernova model. Summary based on what are the building blocks of this scenario for the explanation of the long gamma ray bursts associated with supernovae, and also speak a bit more about not what we have done, but also about a few things that we have still to do in the near future, I hope. Let me start with the concept of binary progenitor of long GRBs. We heard yesterday a very nice summary by Massimo Della Valle about GRB and supernova 1C properties that point to a binary progenitor for gamma ray burst. So just to recall you that GRBs, the long GRBs, are often observed in association with type 1C supernovae. Type 1C supernovae lack hydrogen and helium interspectra, And so it is a special class of supernova that are thought to form in core collapse supernova events. Core collapse supernova of massive stars without helium and without hydrogen layers in the outer in the outermost part of the star. So of course we have to take into account this into the model. But I will come to that in a moment. Here, I would like just to recall the beginning of what is the binary-driven hypernova model is based on the induced gravitational collapse concept. It is starting in 2006. Actually, you see this picture here on the upper right. But it was the first idea presented in Marcel Grossman in 2016. This was Marcel Grossman in Berlin, I think, where actually it was the opposite concept that the binary hypernova.
Sorry, I will ask the others. Sorry.
Okay. So at the time, the scenario was actually the opposite. It was proposed that there was a GRB event that triggered a supernova event in a binary system. So because we observe the GRBs in a temporal and spatial coincidence with supernova, we have to explain both events. So there was a GRB event that triggers a supernova event. Then in 2012, we actually look for what we thought was a more viable scenario also for the binary evolution point of view, that it was actually the opposite. So we changed it completely, and that it was first there is a supernova event, and it's the supernova event that triggers what becomes the GRB emission. And that's all. That's all this talk is about that process. How is the supernova event in a binary system can produce a GRB event? The GRB observables, actually, what we observe the GRB are a sequence of episodes that are all triggered by this supernova event in a binary system. So from the stellar evolution point of view, generally astrophysical point of view, we know that GRBs are related to the collapse of massive stars. This is a general idea that comes from the GRB energetics and from all the properties of GRB. And this is all of us, I think, the entire community is agree with this. That the most massive stars are in binaries, as Massimo recalled yesterday. So as a syllogism, with these two premises, we have to conclude that most GRBs must be produced in binaries. I pose, I don't want to be sharp, so I put it most, not all. We don't know, but actually it could be that all GRBs must be produced in binaries. Our first idea was presented of this scenario was presented in 2012, and the first analytic estimates actually of the viability of this process. And the process is that you have the binary system of a carbon-oxygen star in a binary with a neutron star companion, so a compact star companion in a compact orbit, in tight orbit of a few minutes. And then the supernova event, you see here, this was a sketch of that paper. But the supernova event, again, the supernova material that is expelled gets captured by the neutron star companion. Neutron star can increase its mass, angular momentum, and eventually can reach the critical mass for gravitational collapse and form a black hole. And this process, actually, this black hole formation is what triggers all the next event, the next episodes actually that explain the GRB. But actually, picture is more complex. The neutron star not necessarily reach the critical mass for gravitational collapse, and anyway, it can it leads to again to a gamma reverse, but of a different kind. So there are different fates, different possibilities. I will come into that. I'd like to start from the binary evolution point of view. This was one of the first ideas, actually. This is a sketch from 2015 paper of the binary evolution that we had in mind for the formation of these carbon-oxygen star neutron star binaries that form the binary-driven hypernova. So and actually we end with the conclusion that the binary-driven hypernova must be a subclass of what is known in the literature as a stripped envelope binaries. Because these Taiwan E, Taiwan C supernovae are thought to be formed in the core collapse of helium, carbon, oxygen, or Wolf-Rayet stars. And these stars are thought to be, or the most accepted, the widely accepted scenario for the formation is that they are in binaries. They are in binaries with a compact star companion that is stripped or helps to strip by binary interactions and tidal interactions, by the occurrence of common envelope phases during the evolution, help to strip the helium and the hydrogen and helium outer layers of the star. So this is what actually this binary evolution shows, that you start with the two binaries with masses of the order of 10 and 15 solar masses. Then you have the first supernova explosion in the system. Then, as is usual, the system can enter into an X-ray binary phase where the ordinary star that didn't explode supernova accretes matter onto the neutron star that was formed in the first supernova event. Then the system can go through common envelope phases, and there, at the end of that, of those common envelope phases, the helium and hydrogen layers of the star are expelled. If the system survives to that, then you end with a helium, carbon, oxygen, or Wolf-Rayet star in a binary system with a neutron star companion. Then at the end, you have the second supernova event in the binary life. This is the supernova of this carbon oxygen star that was left here. And here is where we focused. So the binary-driven hypernova model focused on the possible fates of this system here. Second supernova explosion with the neutron star companion. At the time, we put these two possibilities actually that you have, we call them family 1 and family 2. What we know now, this family 1 is what we call the binary-driven hypernova of type 2, while this family 2 is what we call the binary-driven hypernova of type 1. Here, the neutron star form a black hole. In this case, in the type 2, the neutron star doesn't reach the critical mass, and you can end with a neutron star binary, while in this case you have a neutron star and black hole, because from this supernova event you will form a neutron star at the center. So we have a variety. Actually, the system can get disrupted, and you just the system expel, and you will have to runaway stars. This is another possibility. So this binary, this stellar evolution point of view start to evolve, and actually we made start to count so to count the GRB systems, to make a population analysis of the system. This was this ends with a paper in 2016, and I put this picture here because this was discussed in Bego 4 meeting in 2016. You see here from the blackboard, you see our discussion of the binary or the population of GRBs. BDHN, you see here on the blackboard, discussing how many binary-driven hypernova we expected to be observed in the GRBs. GRB observation. We were discussing how to identify them and to estimate their population. And so this end with this paper, when we classify GRBs and we treat all of them, all GRBs as GRBs. So short GRBs, I don't speak about GRBs, short GRBs here, because they are widely accepted that they come from mergers of neutron star binaries or neutron star black hole binaries. And the new thing here was the long bars, the long gamma ray bars that were treated as arises from CO star, neutron star binaries, and these two possible channels in which this is then less energetic than with energy emission that less than 10 to the 52 ergs, they where this what we call at the time, but this what we call X-ray flashes or low luminosity GRBs, while the energy is larger than 10 to the 52 at the high energy GRBs. So in this case, these cases are where before you form a black hole, and in these cases are those in which you don't form a black hole. And we estimate from this analysis and all these properties that you hear by looking at the spectrum and the possible X-ray emission, GV, and all of that GV emission. I will come to that to infer a rate. What is the rate? And how many GRBs you observe per unit volume and per unit time? These estimates are in a local universe, so redshift 0. That Massimo Della Valle was yesterday discussing about that. So we end with similar numbers. You see here the rate of high energy GRBs was let's say roughly about 1 per gigaparsec cube per year, while the low luminosity ones, let's say to give an order of magnitude, is about 100 gigaparsec cube per year. So they are much more much more than the high luminosity, and this is from the BDHN model. This is a natural. I will come to that right now. So I would like to summarize that from a few numbers.
I think we have a problem.
So
yes,
yes,
Jorge, sorry. There was a small cut in the connection, but now it's okay. If you can start again with this slide, it will be nice.
Okay.
Can I ask a question, or do I have to wait until the end of the?
Yes, but I would say
no problem with me.
Okay. Yes, if you can go back to the previous slide. You were showing the APK isocorrelation and declassification. Did you try also other correlation, for example, the correlation in the afterglow, my correlation luminosity at the end of plateau?
Oh yes, we have another paper that in another paper. I don't have the reference right now, but yes, we tried another one after, also for the short GRBs. Yes, but sorry, Maria Joanna, I don't remember the reference right now.
Okay, so maybe yes, if you remember later, it would be nice if you could show. Yes. Okay. Thank you. Thanks.
Okay, so we want to speak to treat here the problem of the binary evolution. I mean, which are the population where these CO carbon oxygen neutron star binaries come from. So let's compare with the population of ultra-stripped binaries. So these ultra-stripped binaries of progenitor of type 1c supernova thought to be 0.1 and 1% of the total supernova events. The supernova rate, you remember this number from the Massimo Della Valle talk of yesterday, about 2 times 10 to the 4 gigaparsec cube per year. It means that the ultra-strip rate would be between 20 and 200 gigaparsec cube per year. Okay. These ultra-strip binaries are thought to form neutron star binaries or disrupted binaries. This is the traditional view of ultra-strip binaries. But as I mentioned, actually there is a subclass of these that can also be more energetic and form neutron star black hole binaries in a BDHN binary driven hypernova of type 1. So the BDH1 rate is 1 gigaparsec cube per year, and the BDH2 is 100. So you can, the sum, so that would be the entire GRB of supernova ratio is very small, so less than 0.5%. This is actually, I agree with the numbers of Massimo yesterday. So we know GRBs occur, there are much less often than supernova because they need special conditions to be formed. The ratio between BDH1 and ultra-strip are between 0.1 and 5%. So this confirms that this variation 1, they are a small subset. This is consistent with the request that to form a variation 1, the binary must be very tight. So you need a short orbital period of the order of a few minutes. I will come to that. And this is a strong request. So you shouldn't expect that this assistance to form quite often. Okay, so this is the first message. And this is different from the variation 2 that are the low luminous GRBs. If you make the ratio with ultrastrip, they can be between 50% and 100%. You cannot be more, but these, you know, there are uncertainties in the rates, both in the rate of ultrastrip binaries, both in the rates of GRB. So we have the uncertainties, but this number, you see the difference between these two numbers, variation 1 and variation 2, tells you that actually that variation 2, that in the variation picture, actually they can naturally form neutron star binaries or disrupted binaries, agree with the ultrastrip population. And this can be compared also with the short GRB rate now. Why? Because if the variation 1 can form neutron star black hole binaries, the variation 2 can form neutron star binaries, we know that these new binaries of compact star objects can merge because of the gravitational wave emission that will make them to merge in some years of the order. I will show that, but 10 to the 4, 10 to the 5 years, something like that. Let's compare with the short GRB rate. So short GRB rates are between 10 to the minus 3 or 5 gigaparsec per year. So we make the ratio between short GRB and variation 1, you end with 0.1500%. So it implies that short GRBs must be dominated by the mergers of neutron star, not by the mergers of neutron star black hole bodies. And I think that I think most of the community would agree with that. In fact, if you make the ratio of short GRB with variation 2, you end with this number, well, about 5%. This can have two interpretations. First, this one I like most is this is the fraction of the carbon-oxygen neutron star binaries that lead to bound neutron star binaries. So it indicates that not all systems will lead to a neutron star binary, I mean a bound binary, but instead you can also have a large fraction of these disrupted binaries. And this is consistent with population synthesis scenarios. I quote here only one paper, but there are many actually, in which they have, you see here different, a binary evolution scenario is similar to our scenario. In their case, focusing on the formation of double neutron stars. So these numbers are interesting, but we have to move to the simulations. So what are the building blocks of the system of this variation from the point of view of the episodes, of the physical episodes and observables in the GRB? So evolution, of course, we have to move to the this supernova explosion triggering a series of processes. You have to simulate that. This was discussed, for example, this is in the PhD school in 2014. Why this is important is because we start to move from the first analytic estimate, very simple estimates of 2012, to make a more involved models involving numerical simulation, starting from realistic models of supernova. And this actually was boosted by the presence of, the addition of Chris Fryer, that is here in this picture you see here, next to you, Carlos. You see here is Chris Fryer next to you.
I recognize now. Yeah.
And then we start to actually, Chris Fryer, I think here, I always want to remember that he changed his mind on the IGC content. They say that he was actually trying to show that this mechanism couldn't work. So he was trying to show that from taking a supernova explosion and putting a neutron star companion, the system, I mean, that you could never get critical mass. But when he started to make his own simulation, he realized that actually this was one of the possible outcomes of his simulations. So we started to move from that, and actually this was the beginning of this paper. So this was the first simulation with a realistic supernova explosion. But this was in 1D, the 1D simulation. You can see here the results of the numerical accretion onto the neutron star companion. So this is from the core collapse supernova code of Los Alamos. I'm making this was a first step further with respect to the 2012 paper, but still has some approximations in the calculation of the accretion rate, in the calculation of the a few things, but already includes hydrodynamics of the accreting material onto the neutron star that you can see here in this sketch on the left side. So it was a fifth step, and it was actually shown that the accretion rate could be pretty high, at the order of 10⁻² solar masses per second. And this means that the neutron star can indeed, in the time of an orbit, roughly, in the time of an orbit, could get enough material to reach the critical mass to form a black hole. Then we move to 2015. We went one step further and put effects of angular momentum transfer that this previous simulation we didn't take into account that effect. You can see here some new simulations of this gray point was the neutron star moving around this exploding material that are the red arrows. The arrows are velocity fields. And you see the plot on the left, you can see the neutron star mass increasing, the neutron star increasing both mass and angular momentum. So moving, these are evolution paths of the neutron star moving into the stability plane, and eventually was able to reach either mass shedding, so the Keplerian limit, or secular axisymmetric instability, so they could prompt collapse to a black hole. Then we show actually that for the most compact binaries, they actually don't only form a black hole, but that they can keep bound. Laura mentioned that in her talk yesterday afternoon. And so actually this, BDH 1, type 1, which you form a black hole, actually most likely keep it bound as a neutron star black hole binary. We estimate the merger time. This was actually a merger time for that short BRB that we actually call ultra short BRB. Well, these are some results, but then we move because we have to move to more involved simulations because there were still some approximations in the treatment, and this was discussed in this meeting in 2016 in Pescara. This is his flyer here, his flyer signing the wall of Pescara Ignite headquarters. And we started to discuss a possible inclusion of three-dimensional simulations into this model. It was a very successful discussion, and actually we were discussing writing actually the first lines of the new numerical code to do that. Thanks to, you see this guy here on the left with glasses. This is Brandon Wiggins that also helped us in introducing this first boost to the code. But then he left the project because he told us he was very involved in his actually was writing a new code for mergers of double white dwarfs, and so he didn't have the time to get involved into this project too. But anyway, we managed to do that with Laura that moved to Los Alamos, and then we are new for 1 year, and with the help of Chris and other students, the new code to do this kind of things. So these are three-dimensional simulations of the binary system. You see the two stars now. Here, both stars, you see vortices of accreting material. What are these two stars? It was the exploding star in the binary, and this is the neutron star companion. At the center of the supernova, you form the newborn neutron star. And you have both of them accreting. So this newborn neutron star gets material from fallback, while the neutron star companion gets it more naturally, let's say. It received the matter from the companion. And we simulated that, including the hydrodynamics effects on both stars, and get the accretion rates on both of them, and also the transfer from mass, angular momentum, and follow the evolution. This is a three-dimensional picture where you see this important effect is the asymmetry that is formed into the supernova ejecta around the system, creating even a sums of low density around the neutron star companion. So you form a lot of what we call the cavity around where the site of that will be the site of the black hole, or the black hole formation. Around it, there is a large region that is like a hole. I mean, a region of very low material, very low density material. So they have a variety of initial conditions that can be exploited for the explanation of gamma ray bars, and we haven't done that up to now. I think that we can exploit more. These are a variety of examples. This is the accretion rate onto the neutron star companion for a variety of scenarios. You see in the first plot, you see different orbital periods here. In the upper left, in the upper right, you see different initial neutron star masses. On the lower left, these are asymmetric supernova explosions that actually Massimo mentioned yesterday. These are actually a very important ingredient that perhaps we should take into account more in our analysis. The possibility of asymmetric supernova explosions is actually, we did some simulations of that in paper of 2019. On the lower right, you see different progenitor masses. So the masses of the carbon oxygen star that explodes as supernova can have different mass, can have different density profile, and this leads to a different fate of the system. And well, it's not shown here, but we did it. We explored different supernova explosion energies from 0.1 to 10-fold, 10 to the 50 to 10 to the 52 of energy of supernova explosion. We have now a new study that Laura showed yesterday, also including non-zero initial neutron star angular momentum. So not only different possible masses, but also different neutron star angular momentum. So in all the simulations of 2019, we always started with non-rotating stars, but this is not necessarily the case. And there are differences if you start with a non-zero angular momentum. This is a plot of the new numerical simulations with increased resolution. And again, you see at the end both stars accreting material, and one of them getting the critical mass to get for a black hole that was the neutron star companion, not the newborn neutron star. So these are the new studies and results. The new studies, these are the accretion rates. On the left, you see this is the fallback onto the newborn neutron star, while on the right plot, you see the accretion rate onto the neutron star companion. This is for different orbital periods. You see the different outcomes. And you see this very unique feature of the binary of the BDHN, this second peak of supernova accretion onto the neutron star, onto the newborn neutron star. This is a unique feature. If you have a neutron star, the newborn neutron star in a supernova accreting material by fallback, usually what you get is a power law, accretion rate that follows this power law, or always a power law, okay? But when you have the presence of the binary companion, actually it takes some matter that would escape and keep it bound to the system, and eventually this can be captured by the neutron star, by the newborn neutron star, and form the second peak of fallback accretion. And actually, this is an important point. we're simulating a spin up and spin down phases of these stars while accreting by the torque of accretion, by the torque by the spin down due to the magnetic stresses by a dipole and quadrupole magnetic field. And well, we are managing to have a semi-analytic treatment of this, even if this is full general relativity result of this. This is on the right. You see different evolution of the rotation periods as a function of time. You see the spin up phase, and then you see the spin down phase of both the newborn neutron star on the left and the right. You see the neutron star companion. This is a new paper actually, where this is the evolution of the change of the gain of energy of both stars, and you see this this complex structure of these different peaks of energy gains of this system. And actually, this is very interesting because we expect this double peak structure. You can see these two main peaks. These two, you see the colors are for the neutron star companion, while the black are for the newborn neutron star. And what you see, you could see in a GRB, the two main peaks, the two higher intensity peaks, one of the neutron star companion and the other one of the newborn neutron star as a precursors in a high energy GRB, or as a double peak prompt emission of a low luminosity GRB. So, and actually this was shown in our recent analysis of 1908-29A, and I suppose U1 will speak about that in a moment. So I don't want to spoil this more, but you have this double peak structure in the prompt of 1908-29A that for which we make an interpretation based on those two peaks that I showed you before, and infer the accretion rate, infer the gain of angular momentum, and show how energy it can be released, and actually that matches what is observed. And this is another example. We would take even more wide binaries on even only a single star. If the binary is very wide, or if the CO core, if the CO star is single, you don't have very much differences in the behavior of the neutron star, of the newborn neutron star. And actually this is shown in this analysis of 171205A. This is a GRB discussed by Luca Izzo yesterday. So we have a picture, an ongoing analysis of that. I don't know if you will talk about that, maybe not, but just to show you here that also in that case, even we managed to make a fully analytic analysis of the spin-up phase of the newborn neutron star. In that case, you see here the analytic and the numerical integration, maybe almost overlapping the two or analytic solution for that.
Jorge, you have 3 more minutes and then to have some questions.
Okay, so the neutron star gravitational collapse, I already mentioned that you can get the instability for gravitational collapse. And so you can divide, you have system in which collapse, then for the black hole, in system in which you don't for the black hole. This is an old plot that we are updating now with Laura. There's an ongoing work on updating where is the orbital period, the maximum orbital period of the system in which you form a black hole. That depends on a variety of parameters, and we are trying to explore most of them and form and will inform to all of you that about those results in a forthcoming paper. We have, of course, analysis of X-ray and gamma ray flares in the GRBs. You have the formation of the electron-positron plasma in the black hole formation. That was the talk of Rahim Moradi yesterday. But Rahim spoke yesterday about the expansion of the electron-positron plasma in the low density region. But you have also this plasma expand also in the high density region also. You see here the hole I was mentioning, this cavity. So you have here along this part, you have the low density, but you have also high density on the borders. And there you can see the breakout of this electron-positron plasma. The transparency along these regions can be observed as X-ray or gamma ray flares. The UPE, this is I jump because this is Rahim yesterday. And so we have the ultrarelativistic emission from the black hole formation, but you have also the high energy emission. The high energy emission is when the neutron star collapses to a black hole. The black hole gets immersed into the magnetic field, previous magnetic field of the neutron star, enhanced by the conservation of magnetic flux. And then this combination of the magnetic field with the gravitomagnetic field of the newborn Kerr black hole induces an electric field, and this electric field is able to in the first part for the UP phase, it gets it at the beginning supercritical and make the formation of electron-positron pairs that self-accelerate, expand, get transparency, and make the pulses that Rahim showed yesterday. Then, as the magnetic field decay by a screening process of the electron-positron pairs, the induced electric field eventually gets undercritical. Okay, and then what happens is a process of acceleration of particles, the particles around the black hole, and emits a synchrotron radiation. I will jump some details here. What you have here some regions, regions where the electric field is outward, and other regions where the electric field is inward. So what we would like to have is in this region accelerating electrons, and these electrons emits a synchrotron radiation that actually in the J region. I'll show here, and this comes at the expenses of the black hole rotational energy. So everything is powered by the black hole rotational energy. So both the UP phase and the GeV emission. So it comes from the extraction of rotational energy of the black hole. So in this process of acceleration, so what is taken out is the rotational energy. So as soon as you see this energy get radiated, I will jump these details of, these are all details of our recent paper with Professor Ruffini and Roy Kerr, of this acceleration of particles in this gravitomagnetic field of the black hole, and get synchrotron radiation. But if we go to the process here, I will jump to this here, and you have this process that bit by bit reduces the rotational energy of the black hole. And you have here this, Professor Ruffini mentioned this in the discussion of yesterday afternoon. This mechanism can be applies both to GRBs and also to galactic nuclei. The only thing that you have to do is to scale the mass and the black hole and the density of the ambient medium, and you get different numbers that match either GRB, high energy emission, or IGN, high energy emission. Well, this is this, and I would like to end with the afterglow. Give me, please, just to show you in a few, we'll jump to the concept. And the synchrotron, the multivalent afterglow, I mean X-ray optical radio emission of the afterglow, is synchrotron emission of the expanding supernova in the magnetized medium of the newborn neutron star. And so you get the energy, the electrons in the eject emitting synchrotron radiation, and the newborn neutron star also injects energy into this. We have an analytic treatment of that actually that you can see in these papers here. And actually have the cases on some feeds here of the 1807-20B or the feed of 1908-29A. I think when you will show that. So I just had here highlighting that, and I will jump this of gravitational wave emission. These are new results that will be useful for population synthesis. Laura showed this yesterday. We are analyzing well the binaries that get bound, binaries that get unbound, and making some analytic formulas for their analysis, merger time, final binding energy, maximum orbital period, and these kind of things. And then this has outcomes in gravitational wave, the possible gravitational wave emission. We have analyzed possible gravitational wave emission also from the transition from the very early life of the newborn neutron star, if it gets initially triaxial, and then make a transition from antriaxiality to axis symmetry. And in this very early evolution, it can make a gravitational wave bars that can be observed more or less following our estimates up to 100 megaparsec distance. And then we see a conclusion, a series of papers. The picture that Massimo showed it yesterday is a summary picture of what is happening in these binaries. And there are, this is not all papers, but a comprehensive list of the papers about the theoretical developments of, in all these summary that I tried to make in this talk. There are things to do. This is a list that you can read. This is a personal list. Okay, this is my personal view of a few things that can be done in the short, medium, and long term. So I will leave it for you. Thank you, Carlos. I'm sorry for the
it's okay.
Extra minutes.
Thank you, Jorge, very much for this talk. And I think amazing job you have done in all these years, huge work and development. It was very nice to recall all of this. And well, now that we have time for a couple of questions, you can raise hands or just turn on your mic.
Well, absolutely unique, this presentation in its historical development, but all the way to the latest interest, which will be continued in the next talk. And I think we have to make an effort to transmit all this document also in written form, because now that we have made this effort in understanding the system, as you said before, yesterday, we have to be open to explain to everyone, and this will be a major effort. But now the building blocks are all there, and the presentation will be much easier. Congratulations again, and I enjoyed every second of your presentation. Thank you.
Okay, thank you. I agree. I fully agree with you. We have to do that. Absolutely. We made, well, we wrote in the last 3 years, we have two or three short reviews of the model that can work as a base for what we can do. But definitely we have to do more in that direction. Thank you.
May I have a question?
Yes, Rahim, go ahead.
Thank you, Jorge, for this nice and informative talk. I really enjoyed. I have two specific questions. One about the neutron star,
yes,
not the companion. What happened that it has in the accretion, it has 2 peaks? And the second question is...
Excuse me, I didn't understand. Can you repeat, please?
What happened that instead of 1 peak, it has 2 peaks, and that late power law will go to another peak? And the second question is that, is there any possibility that this neutron star goes to the black hole formation?
Okay, thank you, Rahim, for this interesting question, because the answer for the first is that I mentioned is a unique feature of the binary. What happened? Imagine when you have the single star without binary, okay, forget about the companion, you have a single star core collapse, okay, you form the neutron star at the center, then there is the rest of the matter try to escape from the system, okay, that's the matter that will observe a supernova, make the supernova, but there is part of the matter that falls into the gravitational, make the fall back, okay, okay, you have the single fall back. In that case, you have a single power law of the accretion rate decreasing with time in that kind of configuration, okay? The rest of the matter can freely escape. What happens when you put the neutron star companion? You put the neutron star companion, part of the matter of the supernova that would escape actually fall into the gravitational field of the companion, okay? So that material cannot escape and gets bound into the binary. And what happened actually is that some of these particles get into the gravitational field of the companion, make a sort of a loop around it, and when they come back, get captured by the neutron star, by the newborn neutron star. Okay, and all those particles that actually otherwise would escape, that form that second peak of accretion, right, on the newborn neutron star. And actually, this is very interesting, your second question, because this is related, that in some simulations, we found that actually also the newborn neutron star could reach the critical mass and form a black hole. Because of this second bump of accretion can make it to gain additional mass and eventually form a black hole. But there are very, very, very special cases in which we found that, but we found them.
Yeah, and this can have some specific observational effect that you can predict. It would be interesting.
Yes, that could be done. We didn't do that yet, but that can be done actually. This would form a binary system of two stellar mass black holes.
Yes. Okay, thank you.
Okay, we have time for one more question. Okay.
Maria Giovanna, maybe you had a question. Or many questions.
Yes, Maria did a question before. Yes. I think was
yes, I have to look to that reference to Schumann-Johann analysis with the other using the additional different displanes of peak ISO, and we analyze that also with the luminosity of the plateau. Actually,
okay.
We have that in another paper. We'll send it to Maria Giovanna.
Good. Okay. So if not, we really thank Jorge again for this talk, and we shall move to the next talk, which is Yang Li.
I stop my sharing. Okay. Thank you.
Yang Li, if you can start to share your screen.
Okay, let me try. Can you see my screen now?
Yes.
Okay, good. This time is a success. Okay.
Good. So you can start. We have Yang Li from ICANNET. He will talk about the 7 seals of the binary-driven hypernova burst.
Okay, thanks for the introduce. Okay, I'm going to talk about the 7 seals of the BDH burst. As introduced a lot of information for the BDH models in the first talks by Professor Auger. We know that there are several different physical processes predicted by the BDH models. Usually we can say that the different physics processes might have a different temporal and spectral property in the observations. This is the left picture show that show a cartoon picture show that how a BDH burst works under the framework of the BDH models. So why BDH model? There are at least 2 significant advantages. The BDH model is based on a binary system, star system. This is a binary star system is common observations as compared to single star system. The second reason is that BDH GRB's model can be electron experiment associated with the supernova explosion. So my talk today related to several projects in our team, part of published, some others have not published yet. So the general approach for the data analysis especially for the spectral analysis, we used is the Bayesian plus monocolor Markov method. Use the package namely 3ML. This package is developed by the Fermi team a few years ago. When we perform a Bayesian analysis, we should see the prior information. The prior information, we use the typical value from the Fermi observations. For the more detailed information, you can find in these papers. So we're starting our research on this force, Lighting 114C. The first force detected by Fermi with a type emission. Also, we have low BDH GRBs as predicted by the BDH model should including these components. The first is the UPE phase related to the formulation of black hole. Then follow a neutron star rise. Then follow the UPE2 phase, we call the main UPE phase. Then the cavity. Later, the hard and X-ray, soft X-ray flares. At a later time, we might be observe GRB and the sublowar associated emission in the optical band. Then we also might be observed multiple lines optical emission, like the sub-tower optical emission, gel optical emission, X-ray optical emission. This is the picture show the lighting 114C. We already observed this episodes or we call components. We initially we observed the UP1 phase. This phase the spectrum we can fit in bicycle fitting can be bicycle fitting by a catapult plus a thermal black body component. Then we observe the neutron sunrise. The spectrum can be fitting only by catapult model. Then the UP2 phase, similar to UP1 phase, we also find a thermal component. Then follow cavity. Then at late time we also find a GRB sublowar associated emission bump at around 2 weeks. And also we observed the sub-tower optical emission and the gel optical emission and the X-ray optical emission. This force is very close. The redshift is 0.4 and the duration correct to the rest of frame is 18.1 seconds. Then because we found that the UP2 phase is very bright, then we try to perform a detailed time resolution analysis. We perform a 5 successful iterations. For each iteration, we go short time scale and look deeply to look the spectral characteristic of the UP2 phase. Then we found the same similarity structure, namely the spectral perform the similar behavior. We summarize our plots, put out our plots together in this figure and summarize all the information of the fitting result in the table, and including all the fitting parameters. We found the temperature, even the cutoff energy, and similar between the different time scale of the attention file. Then we also look in the another boss 180722B. This is another boss with type emission. We also observed all the 7 episodes. similar to the Lighting 143, we also found the UPE1 and the nucleation sunrise and the UPE2, then cavity and also the hard X, soft X flare. And we also
sorry, Lian Li, I think we have a connection break. If you can, let's wait some seconds if we can restart. I think we are okay now. So can you repeat from the last minute, please?
Okay, sorry. Okay. Is this from this is okay? This is
Yes.
Another boss with type emission, like 180720B. We observed all the episodes in this post. This post is also very close by with the redshift 0.6. T lighting duration in the rest frame is the lighting 29 seconds. We similar to lighting 143, we observed the UPE1 phase, nucleation sunrise, and the UPE2 phase. Then the cavity, X-ray harder and soft X-ray flare. We also observed the multi-wave lines afterglow emission, like the sub-tab emission afterglow and X-ray afterglow and tab and gel afterglow emission for this post. So we also we also performed the 5 iterations for the UPE2 phase for this post, because the UPE2 phase is also very bright, similar to the lighting 143. Then we also found a similarity structure for the spectral analysis and summarize our information in this table. So it is interesting. This is the first pause detected by Femi this year. We missing a lot of components. This pulse has a very high redshift with redshift is equal to the 4.6, and the duration correct to the rest is 22 seconds. We're missing the UPE1 and the UPE2 phase and the cavity, hard and X-ray flares. Also, we miss the GRB sublower associated emission, also tab afterglow. This is the spectrum for these 2 sparks. We didn't find a thermal component, so that's why we miss the UPE phase. So we also compare to our result. We also looking the another very interesting was the OLI 0423. This was with the highest redshift, and the T lighting is very the duration is very is only the 0. Is less than 1 second. We nearly missing all the components. We only observe the nucleation sunrise and the X-ray afterglow. So this is our GCN result published our result on the GCN. We found that the 220101A. We found that this can be identified the BDH1 class. We also found another post. This post also can identify BDH type 1 BDH1 post type class. Okay, my conclusion is to find 7 different components in the BDH1 GRBs, such as the lighting 43 and GRB 180720B and 2201A and 0423. And the further the distance, the field, the episodes are observed. This observation can be well explained with the framework of the BDH model designs. And finally, I wanted to say something about I'm very enjoying with the collaborating with the Professor Dolati Maria. We have exceptionally a lot deeply collaborated with each other. Okay, thanks.
Okay, thank you, Yanli. Okay, we have time for different comments and questions. So,
well, maybe you can show again the GCN which started all this process.
Okay.
Yes, and certainly the starting point was that 220101, here represented in red, as the most powerful X-ray afterglow of all the other BDHN1, which we had studied before, in particular in 190114C. And then we were challenged to look also to the farthest possible BDHN1, which was discovered in our group by Luca Izzo. And this led us to the very, of course, a very intense analysis of the characteristic seals. Maybe we can have again the summary of the different sources that you have just shown. The summary table with the red part, yes, yes. And we have seen the transition as a function of Z. And one of the very interesting point is that the T90, the duration of the signal, changes very much with time. Did you show the T90 of each one of them?
Yes, for example, this one showed this one here.
Up there.
Yes.
Therefore, if you compare the GRB for 190114C, for 190114C.
Yes, 190114C is here.
Yes.
190114C is
the T90 is 81.4 seconds. Then if you go to the next one,
this one.
To the next one, 180720B, the T90 is 29.5, but simply because that source is less intense than the previous one. And then if you move to the most interesting one, the one which changes with Z, you find that the T90 go down to 20.86 seconds. And finally, if you go to the last one, the T90 is 0.8 seconds. And this behavior was really predicted by Petrosian and collaborator to occur. But here we give the physical reason why this happens. And it's not possible to understand the system just by a single star model, which is traditionally adopted in the collapsar model. But all the 7 seals which characterize a BDHN1 are needed to be identified. And this needs a binary system formed, like Orge used to say, by the CO core and the companion neutron star and the new neutron star born in the process of the supernova event and All these explain the 7 seals. But what is very interesting is that the number of seals changes with the distance. And this is the key point of your table. Can we see again the table? Yes, maybe you can scroll from one to the next, going from 1807 to 19 to 21, and yes, and to show how the number of seals changes, and at the same time, the lifetime, the T90, also changes. Well, you did an enormous amount of work. Let's go back to your paper of 2020 in the spectral analysis study, and we are grateful for you of this immense work that you did in spectral analysis, which finally is leading to a much deeper understanding of BDHN1 as a function of Z. It's not trivial. It is like if nature would like to not allow to learn about the approach of the GRB to the cosmological singularity. And at the same time, the very, very exciting point is that the 7 seals have been understood, and the situation is not so hopeless in the sense that it's true that we cannot find the seals for Z larger than 1, but we have learned a machine which is at the background of the BDHN1 at Z smaller than 1. And this sort of physics, which is the UP phase, this is the crucial point, the self-repetitive process going on very short time scale down to 10⁻⁹ seconds in the UP phase can be scaled, like Jorge just said previously, to the case of very large black hole of 10 to the 10 solar masses, like in M87. And the characteristic scale, which is 10⁻⁹ here in the UP phase, becomes of the order of 10 seconds or longer. And this is very exciting. We are learning for the first time the physics of black holes thanks to BDHN1, and we will be able to extrapolate to active galactic nuclei all this physics. And clearly, the Z dependence of this result is very important. I just wanted to make this general comment.
Okay, thank you.
May I make a quick comment also on this?
Yes,
Carlos?
Jorge. Yes, please, Jorge.
Okay. First of all, I would like to thank Lian Li. This is a really, really nice job you have made with this.
Thank you.
And of course, the fact that we are confirming actually our picture at a very light redshift, this means that we at some point we have to attack this problem, and that's why I spent some minutes today also speaking about the binary stellar evolution that we expect for our binaries, because the fact that we are confirming the presence of them at very light redshift will actually say something about the binary evolution at very high redshift, because we need to form our binary. The binary needs the time to evolve and to form the compact binary of the CO star or helium star or Wolf-Rayet star in binary system with the neutron star companion. So actually, it's a really nice problem to to attack from the binary stellar evolution point of view. So the formation of these binaries at very light redshift. So this is my comment on this. Thank you.
Okay, thank you.
Thank you. Let's see, we have time for more questions. Let's see, we have some other question.
Yes.
I have a general question, maybe a bit technical question for Liang Li. So okay. I'm not from this area of research, but I would like to know this, when you show in the beginning the Monte Carlo approach you were using to fit all these different features. So the question is, how many free parameters you have or you are using to fit all these different?
This depends on which model you use. For example, if you use the bundle function, there are only 4 parameters. If you use the color power, there are 3. If you use the color power plus breakpoint, there are 5 parameters. This depends on which model you use.
I see, but could you comment? Yes, but on the free, how is the relation between the free parameters and the underlying physics of your features?
This is we use statistical naming some statistical naming the DIC. Okay, some statistical like here, ICB is something like this. DIC, how to say this? I forgot the full name. So use some statistical to check.
Inference criterion.
This statistical information is consider the free parameters. You understand?
Yes, I know. You are saying that this inference criterion differentiate between the different models which have different amount of parameters.
Yeah, yes.
Yes. Okay, but the free parameters, so you can directly relate with the different physical process you are considering in these first seconds, or
yes. Usually we think the UPE phase we should including a thermal component, yes, the different physicals. We think yes, and for the Newton arrays the spectrum is different because we didn't observe a thermal component. For the UPE2 phase we observed the thermal component. For the cavity we also didn't find a thermal component. Namely, the initial we found a thermal component, also we found a line thermal emission component. Then the Newton arrays we only observed the line thermal emissions. Then we found a UPE2 phase also a thermal component. Then disappeared, something like this. The different emission component, different related to the different physicals, different physical mechanism.
I see. And one more question. And considering you ran a Monte Carlo, so you have an island of probabilities. So you find some degeneracy among these parameters between for given, let's say, observable, or you have quite well resolved. I mean, quite well means and the probability without degeneracy.
Sorry, I don't know why clear your questions again.
Okay, no, because Monte Carlo sometimes allows you to understand.
Monte Carlo only is found the posterior. This is nothing to do with the how to say with the yes. This Monte Carlo means found the posterior, the density of the posterior. Then we look the most probability area to assume this area is our best parameter values. We choose. Do you understand?
Yes.
How to say? How to?
I understand. So I just wanted. And my final question is the following: Could you run, for example, compare this approach you have will allow to compare with a different model for the interpretation of the data and compare between the different posteriors?
Okay, it's not a different model, it's a different approach. like we use the basin, there are also transition portion, namely the frequency.
Yes, but I want to know if, for example, you can compare with other paradigm for interpretation of the data in order to compare, for example,
Yes.
To show the comparison but with the same algorithm.
Yes, of course, you can compare, you must compare, in the sense that in order to fit the 7 seals, you need absolutely a binary nature of the system, which has different physical components, which we have identified by their spectra, namely the UPE, and each one of these has a significance and identify the source. But you cannot fit any one of these data with an object, for example, which is coming from a collapsar and a single ultra-relativistic jet. There is no way to fit in that way. Therefore, the answer is yes. We have now very detailed description of the system, of the binary and different components, the CO core, the neutron star, and the companion neutron star, and all this detail. And thanks to the spectral analysis, which has been done by Liang Li in our group, it can be completely defined. But certainly it's alternative to the other point of view, which cannot fit the data. But I would like to maybe Jorge has a comment.
Yes, Jorge want to comment, please, Jorge.
Oh,
Thank you.
yes. Yes, thank you. Okay, yes, I have a question because in one of the seals I see GRB supernova connection. I want to ask you if this you refer to the optical supernova. To that part, I suppose. So I want to ask you if about the optical supernova of the optical counterpart of the afterglow. Concerning that, if you expect some change with from the James Webb Telescope, and did you expect that James Webb Telescope would put across there of a yes into that, maybe to observe some of these systems at high redshift?
Okay, I would like to touch on the same topic. But this is really very exciting. If you look, Jorge has pointed out something very crucial, that we know that the binary system evolved in the different era. And if we, that he has shown, therefore, in principle, looking back at IZ, okay, looking back at IZ, we should see this object evolving in time from Z equal 8 to today. But the answer that we have made is that you cannot do the job using Lat, Fermi, and because only one seal is left at IZ. But I think very challenging, I'm just dreaming about what the James Webb will allow to do to uncover that indeed the very early phases of the binary at IZ are the one which we cannot observe through the Jeff radiation and so forth, but they can indeed be observed by James Webb and confirm all the binary nature that we are postulating in the early phases at IZ. This is definitely very exciting. I would like to have a comment by Jorge on this.
Yes, I think that study can be done because we can analyze that. We have very nice proxies of all emissions. So we can actually infer what can be our prospects for James Webb Telescope. We can do that. I don't think that's difficult. I think that this is in our expertise to do that. I think we should do it.
Actually, I have done this. And I'm doing with Yelan. I have finished the half part for the spectroscopic part, and it seems for James Webb.
Who is speaking? Who is speaking?
Wang Yu is speaking.
Yes.
Yeah. So for the photometric, we haven't done, but I think it will to a very, very high redshift. And for spectroscopic is the upper limit is 2.5, redshift 2.5. I think I need to finish this work in this month.
Well, I think this just show one of the hottest topic that is going on in our group. We have said enough to interest and to say that we don't want to not to disclose our work, but on the contrary, we have said the three very important contribution of ongoing work. The one that has just been summarized by Liang Li, the one that has proposed Orge and is worth to continue, and also the ongoing work of Wang Yu. And by that time, this time, I think these are the three different approach going on contemporary in our group. And let's go to the future, and maybe we can have a break before, but let's the chairman decide before the contribution of Wang Yu.
Yes.
Go to Wang Yu and then to have the break.
So yes, we could decide among all, because the point is that we have one more talk until the coffee breaks according to the program, which is Wang Yu now in the next minutes, and then we have a huge break till lunch break. So either you prefer to take one short break now, coffee break, because then we will have a free time after Wang Yu, and we come back maybe in 10 minutes, 15 minutes.
Yes.
Yes. Okay.
And then we have a further discussion later.
Okay. So we will meet in 15 minutes in yes. 10:45 and with Wang Yu. Thank you.
Thank you.
Thank you, Liang Li. Okay. Hello, everyone. I think we are back from the coffee break. And I will ask Wanyu. Yes.
Hello, Charlie.
Hi, Wanyu. Nice to see you. And
Nice to see you.
thank you. So, yeah, if you want to share your slides,
Yeah,
we can
let me
start.
share my desktop. So it's okay.
Yes, but it would be nice you can put full
Yeah,
screen.
I will. Because first, I want to say something about the question that discussed in Liang's talk about the observation of James Webb for the supernova. Let me show one figure.
Okay.
To answer the question. This one. So this one, the x-axis is the wavelength. So it is 10 to 4, more than 10 to 4 is in the infrared. Yeah, so most part is in the infrared, and x-axis is the flux density. And this gray dots, triangle, square, diamond is the limit of different satellite. So it's marked here, Gemini, James Webb. So James Webb has the best resolution around the 10 to minus 8. And these colorful ones, the green and the blue, the green is the optical part and the blue is the almost infrared part in the rest of frame. So at a different redshift. And this line, I take the supernova 1998 BW as the example. So it's a solid line. And the shadow is the lower limit and upper limit of all the GRB associated supernova. So the range of the supernova luminosity. So you can see at the redshift 2, the third one from up to bottom, at the redshift 2, it's in the James Webb's limit. It's they overlap. And at the redshift 2.5, only the brightest supernova can be observed by James Webb. But this is a spectroscopic. So for photometric, we can have a deep distance. For spectroscopic, we have to see each line, but for photometric, we do the integration. So the redshift will be much higher. Okay, now I go back to my talk.
So you can, when you have shown, you can extend at least one digit in redshift from the previous expectation.
Yeah. Yes, before for optical, we can only observe the redshift less than 1.2 or 1. I think the furthest supernova ever observed is 2 point something, and only 2. I think more than redshift 2. And people are looking for the high redshift supernova, but the GRB associated ones are the best ones because we know its location. It's bright. We know the location. We know the time. So the space-time coordinate is fixed, and we don't need a lot of telescopes time to do a survey to look for it.
Nice.
Yeah. So I'm how to minimize. So I'm going to give a talk on the GRB 1908-29A, a showcase of binary-related evolution. So this is we have the model, BDHM model, and the BDHM model has a lot of subclasses, and this is one of the subclasses. So this GRB 1908-29A is the fourth closest gamma burst to data. Its redshift is 0.08, like, so it's less than 0.1, so it's very close by. And this GRB, because it's very close by, and it underwent one of the most extensive observation campaign. So including the Fermi, the Swift for the KEV and MAP observation, and a lot of satellite and telescopes like GTC and the ground for the optical and infrared observation, and especially the HESS, the very high energy HESS, observed the TeV ultra high energy photons. And this figure shows the pumped observation observed by Fermi GBM. So the light curve shows two pulses. The first pulse starts to rise at -1 second, peaks at 1 second, and fades at 8 seconds. So in total, like 9 seconds. Then after a time gap about 40 seconds, the second pulse rises. And this second pulse has a duration like double of the first pulse, and it has more photons. So how many more? Like 5 times more photons. So we first do the spectral fitting of these two pulses. And we did it by the Bayesian analysis with the Markov-Chain Monte Carlo. And also we double checked by implementing the Fermi GBM data tools. So for the first pulse, the cutoff power function gives a best fit of the power and band function and others. And we also tested an additional black body component to the upper model, but it did not lead to a statistical improvement. So the fit of the spectra, the power index is minus 1.15, so it's a very typical value, and the peak energy 144 keV for the first pulse. The energy, integrated isotropic energy is like 5 times 10 to 49 erg, so very low energy, and the luminosity divided by this 10 seconds, it's in the order of 10 to 48 erg per second. The second pulse is best fitted by a band function, by a very strange band function. So you see it has a bump around 10 keV. So this band function gives a very low peak energy at 13.58 keV, very low. This almost touches the lower edge of the Fermi GBM's energy band. And because of the small amount of data energy before, lower than this EP, lower than 13 keV, the low energy index is not well constrained. In fact, here I wrote 0.5. Actually, it's 0.5 plus minus 1. So it's not constrained. But the high energy index beta equal to minus 1.53. This is a typical value. And the total energy in this second pulse is 2.5 times 10 to 50 erg. And the average luminosity is about 2 times 10 to 49 erg per second. So we can see, though the second pulse is more energetic.
Yuan, can you speak a little bit louder, please? Maybe sometimes
louder, yes.
A bit louder. Thank you.
So though the second pulse contains more photons and more energetic, but the average photon energy in the second pulse is lower than the first one. Because the first one peak energy is 144, and the second one is only 40 or only 14. So now go to the next one. Now this is a light curve, a full light curve, including the data from HESS. You can see in the middle only 5 yellow points, so from 10 to 4 seconds. And the energy is from 200 GeV until 40 eV.
Can you indicate with an arrow the points?
I cannot. I think it doesn't show my mouse, so I can only speak by words. So you see the HESS is yellow cross in the middle from 10 to 4 seconds to 10 to 5 seconds, only 5 points. Okay. And the Fermi GBM is, you can see from the very beginning, the orange dots. The orange dots very beginning. And the energy from 10 to 1000 kV I plotted. And for the BAT is this triangle also from the beginning, this triangle and with the arrow bar. So you can see the BAT is almost overlap with the GBN. Though they have different energy band, but the shape should be similar, and actually they're similar. And for the optical is the green one. The green one from 10 to 4 seconds, you can see the observation of I band from GTC. Though there are some red points, the red points are extracted from the green one, because using the green one, then minus the optical from the synchrotron. Then we have this red one. This red one is the supernova component. And in the below, we can see the also the blue one is the longest one. Blue is the X-ray. So we can see the X-ray is parallel to the Hess. Also, it's almost parallel to the optical. So optical, very high energy, and X-ray, their light curves are almost parallel. Also for the armilla, for the radio, so it's parallel also. Now this kind of light curve, the shape of the light curve is almost typical. Though we can see a small rebrightening at like 10 to 2 to 10 to 3 seconds of brightening. This has been seen in some GRBs, but not frequent. And because it's very wide range of the radio, optical, X-ray, very high energy observation, especially this high energy observation by Hess, this GRB has become a very essential source to examine a variety of models. So here I listed some papers. So this first one by Abdallah, they presented the Hess observation of the very high energy photons. And they talked about the shape of the light curve is similar to others. And they also talked about the standard Photoshop model was there applied to the afterglow, and it shows its difficulties in explaining their observation, the high energy observation. Then the second paper by Rhodes et al. Shows the radio observation, what is explained with the synchrotron Photoshop model. Then Hu et al. Presented the optical observation, and they analyzed the multi-wavelength data and compared with the GRB 180728A. And Frazier et al. Modeled the optical and X-ray observation in afterglow by the synchrotron for the model, for Photoshop model, and they modeled the very high energy observation by the synchrotron self-confidence category. Zhang et al. Interpreted the very high energy observation by the external inverse confidence scenario with the seed photons coming from the prompt emission process. And this is Chang et al. They analyzed the various episodes of this burst and they concluded that the shockwave break model could not explain the entire burst. And Seto et al. Proposed that this burst was viewed from an off-axis angle. Then Zhang et al. They proposed that the interaction of the hard X-ray photons in the first prompt pulse with the dusty media produced the second prompt pulse. And also the very high energies produced by the synchrotron self-confidence. And the teacher focused on the early afterglow. Their multi-wavelength study reported the existence of both forward and reverse shocks. So all the above articles, they present detailed observations, including the radio, optical, X-ray, very high energy, and it gives a variety of interpretations of different emission episodes. But they all generally assume a single progenitor and anti-relativistic shock wave. Also, we know the conventional concept of camera burst postulates that the fiber model postulates that when a core of a single massive star collapses, a relativistic shock like outflow forms and precipitate. The internal shock in the outflow produces prompt emission, then outflow interacts with the interstellar media, generating afterglow via the synchrotron process, as well as the very high energy emission via the synchrotron self-content process. So for our approach, we have a very different approach. We started by focusing on the nature of the binary project, and far from describing a single leading on relativistic process, we emphasize the existence of a number of episodes with different emission processes. So we evidence first that for this JABI, the two prompt pulses observed related to the progenitor of the binary components. Second, the synchrotron electromagnetic radiation is from the mild relativistic expanding supernova ejector. So instead of this anti-relativistic jet. And also we have, and third, we finally address the appearance of optical supernova. Because in our model, we have a supernova explosion, so it's very natural to have a supernova. So therefore, in our approach, we model the sequence of the physical and the related radiation process and focus on individuating the binary properties that play the relevant roles. So in short, we are not using a single shock wave, but with the physicals in different episodes. Now, Jorge gave a very complete review of the simulation and the model of this binary system, that the evolution of the binary system. Now here, this JABI explained by, also we have the same initial state that a neutron star and a CO core. But for these two stars, their separation is relatively far away in our scenario. It's more than 10 to 12 centimeter. So in this sense, the equation from the supernova ejector, first we have two stars, then one star explodes to have a supernova. The supernova ejector will be equated onto the companion neutron star. With this very large separation, the neutron star companion neutron cannot equate enough mass to collapse to a black hole. So finally, we have a new neutron star and a massive neutron star. So usually at the for the supernova explosion, that the most of energy, like 10 to 53 of energy is deposited in the neutrino, and a few percent of energy goes to kinetic energy of supernova ejector, about 10 to 41 to 10 to 42. Usually, and for the JABI associated supernova, always like 10 to 42 in order of 10 to 42. And this ejector expands outward at a velocity of 0.1 c averagely. And the lower density outermost layer has a higher velocity, and while the inner side they expand with a lower velocity. So after a few minutes, so this expansion. So I'm talking about this picture, the simulation done by Lola. So this is an ongoing process. So we can see the supernova has been exploded, and the supernova ejector has reached the companion neutron star on the right side. So first we have this matter accretion onto the companion neutron star, the green dot surrounded by the red color. And this accretion produces the first pulse on the top left. But in the meanwhile, there are some matter falls back leading to an accretion process on to the new neutron star, so the blue part. This fallback accretion is significantly amplified by this companion neutron star. It alters the companion neutron star, alters the trajectory that a partial of the supernova ejector that flows back to the new neutron star. And this accretion rate on to the companion neutron star is about the 10 to minus 3 solar mass per second. And also this fall back onto the new neutron star almost in the same scale, I think. And but it only lasts for some tens of seconds, because for this high accretion rate, it should be supplied by the very high density and slow moving part of the supernova ejector. This time, how long the accretion takes and how long the observation we will observe, it depends on the separation by separation a lot. And with this very high accretion rate, the energy release will be like 10 to 48 to 10 to 49 per second. This is what, so the time scale and the energy is exactly what we observed. Also, I want to say, also Jorge explained in his presentation that is the accretion onto the new neutron star actually has two components. The first is the typical fallback matter, fallback accretion, the same as a single star. After it bursts, it has this accretion, fallback accretion. This accretion rate is small, and the peak luminosity is less than 10 to 48 per second. So it can hardly to be seen for this cosmological distance. So only because of this binarity, because of this disruptor or this by the companion, this fallback matter induced by the companion neutron star, it induces a higher accretion rate. Then we can see, then we can have a higher luminosity till 10 to 49 per second than to be seen. So this is a characteristic of only for the binary model. So from the simulation, the short time separation, about 40 seconds between the two pulses, suggests that a binary period of the order of tens of minutes. This is in agreement with the energy release in the point emission of these two pulses. For an optical period of like 20 to 40 minutes, the peak accretion rate will be like 10 to minus 4 solar mass per second. So this transfers into the accretion power of 10 to 49 per second, assuming 10% of the efficiency. And for the energy release powered by rotational energy of the neutron star, which first is spin up by the accretion. For example, a 1.5 solar mass star and with accretion rate 10 to minus 4, 10 to minus 5 solar mass per second, it implies the spin up rate is about 40 hertz per minute. So this simulation shows the neutron star accretion, and the neutron star accretion peaks in about 1/10 of the orbital period. So the neutron star finally will have a frequency about 80 to 100 to 160 hertz. This implies the rotation power of the neutron star is like 2 to 5 times 10 to 48 per second. So here we can see that the accretion. So we have the energy directed from the accretion, and also we have the energy released by the neutron star. The neutron star will spin down, then it has a very fast rotating, then it releases its rotational energy. These two energies, they are quite similar. So here we can, let's have a short conclusion that the first spike, the first pulse is produced by the accretion onto the companion neutron star. Then the second one is the accretion onto the new neutron star. The fallback accretion onto the new neutron star. And this fallback accretion will continue as the source of the energy that powers the afterglow, so as well as the spin down of the new neutron star. The afterglow is produced by the mildly relativistic expansion of the supernova ejector in the presence of the magnetic field of the new neutron star. And we know this synchrotron model is widely adopted in the JAB physics. So we also adopted it for the afterglow, but with some different specifications. So first, we assume the ejector expands at a constant velocity, at a low velocity, 0.1 c or around. The fast part slow, around 0.1 c. So the radial evolution evolves as a linear movement, and the traditional model always considers an ultra-relativist shock wave, which has a very, very fast velocity than ours. So, and the second is our magnetic field is from the new neutron star. In agreement with the pulsar theory, we assume that at a large distance from the new neutron star beyond its light cylinder, the magnetic field decreases linearly with distance. Now, this implies that the magnetic field strength felt by the expanding ejector evolves with time, as the formula is B formula. So we have a changing B, not a constant B, or not as because the traditional model always assume that a given percentage of the kinetic energy, like 0.1%, will be converted to the magnetic field. And many of the simulations always consider a constant B, but here we have a evolution B. And the third, that we have the fallback accretion to have energy injection from the fallback accretion of the new neutron star. So as this formula, L injector. And then also we have the energy injection from the spin down of the new neutron star. This energy injection will dominate the late time evolution, like more than 10 to the 4th second. And then we consider the dipole and the quadrupole two components. Here we know for a newborn neutron star, it may have the quadrupole components and a strong one. So this is the fitting. So our fitting shows that a new neutron star spinning at 8 millisecond period, and with a dipole field of 5 times 10 to 12 Gauss, and a quadrupole field like 10 to 14 Gauss. And also the velocity of the supernova ejector moves at the order of 10 to 9 centimeter per second, can generate and can well fit the observation. We have these 6 lines are our numerical results, and the points are the observation. So we fit the X-ray, we fit the blue one is optical, but not the blue bump is the supernova, it's another story. And we also fit the, here we show 2 bands of the radio. And this burst has a very high energy emission. And for our previous the synchrotron fitting, we cannot produce it. So synchrotron fitting is the black line on the left side. So also we tried to apply the inverse Compton in our model. So that is the upscaling of the inverse Compton increases the energy of the photons by a factor that equals to the square of the electrons Lorentz factor. Therefore, the spectra on the right side, it has a similar shape of the synchrotron spectrum on the left side, but still the synchrotron self-Compton emission cannot explain the Hess observation, because we can see it peaks at a few hundreds of MeV, and it cuts at less than 10 GeV, and the luminosity is much lower than the Hess. Therefore, we concluded that neither the synchrotron emission nor the SSC can explain the very high energy emission of this burst within our model of the emission from the supernova ejector. But because the similar power law behavior of this very high energy and the X-ray light curve, this suggests that the very high energy could be related to some transient activity of the new neutron star. But at this moment, we have not explored this possibility in detail. We also noticed that the Hess team, in their paper, they expressed a similar conclusion that the traditional afterglow model, including SSC, does not explain the observation. And they expected a multi-zone emission model because we are using a multi-zone emission model. And we haven't developed for this high energy emission. And this BDH model naturally contains a supernova. We know it. And the supernova produced like 0.4 solar mass nickel. Its radioactive decay energy is emitted mainly at an optical wavelength with a corresponding flux that peaks around 13 days in the southwest frame. So here we can see this red part is the finally conferred supernova by GTC at 10 to 6 seconds. It's very low redshift, so almost 13 days. Okay, so here we conclude that the first GRB 1908-29A has a close distance of redshift 0.0785 was observed by multi-band telescopes and satellites on the ground and in space. These detailed observations have given us the opportunity to find the emission that corresponds to the episodes expected to occur in our BDH2 model. The second, the initial X-ray pulse of energy 4 times 10 to 49 erg, and the second pulse of energy 3 times 10 to 50 erg represent the supernova ejector accretion onto the companion neutron star and the new neutron star. Third, we explained that the radio, optical, and X-ray afterglow emissions as due to the synchrotron radiation from the neutron star ejector expanding in the magnetic field of new neutron star. The new neutron star continuously injects energy into the supernova ejector from fallback accretion and the spin down only to the magnetic braking. From the fitting of the afterglow synchrotron emission, we infer the new neutron star spinning at 8 millisecond period with a dipole field of 5 times 10 to 12 Gauss. Okay, so I finished.
Okay, thank you, Wanyu, for your talk. And we have some 10 minutes time for questions and comments. So let's see.
I can.
Yes, Maria, please.
Yes. Thank you for your very nice talk, and I have some comments in relation to the review that you were mentioning in the literature about several papers that were discussing the very high energy emission. I want to point out, I wanted to point out that there is also another paper of Frey et al. 2022 that we recently posted in archive, in which we analyzed the observation from Fermi-Lat GRBs, and we used the synchrotron self-Compton. So I think you may want to have a look at this and also the results, because we did a statistical analysis for the full sample of the Fermi-Lat GRBs. And another comment that I want to run is that for a few cases of GRBs that are observed by Fermi-Lat, actually there are three cases: 0902b, 160509, and 090510. They have indication also of the plateau emission, and we studied in a paper in which I'm first author in 2021 the external forward shock. So I think this is useful probably for you
Yeah,
to have
it's
a look.
useful. I will take a look at those
Yes.
papers. Thank you. Thank you.
You're welcome.
Okay, thank you, Maria. So we have time for more questions.
May I have some question,
Yes,
Carlos?
Jorge. Yes, please.
Yes, about this comment of Maria Giovanna. So this new paper that you mentioned with the Nissim, that of 2022.
Yes.
So you include also 1908, 29A there. I mean, interested to know if you managed to explain the TV emission with synchrotransfer content for that source.
On that paper, not, but we are working on another paper, and hopefully, we can tell you a little bit more in, a month or so. But
Okay.
thank you for your question. Yeah.
Okay.
Okay, thank you. Let's see. There is another question or comment in the audience. We don't see any right hands.
Yes, actually, I would like to comment on the first slide of when you about the James Webb Telescope stuff. Just to tell to want you not to focus only on the supernova, but also on the optical counterpart of the afterglow, of the synchrotron afterglow, that we know can be at higher can be more luminous than the supernova itself, and so that could be pretty well observed up to higher ratio for James Webb Telescope.
Yeah,
I think.
yeah.
Okay.
Yes, thank you. We are considering this. Thank you.
Okay, I have a general question. Maybe if there is not, let's see, if there is no right hand. No, there is no. So I have a general question. I don't know if it's directly related to this talk of you want, but maybe for general modelistic. Do you have some estimate? Let's say in the cases where you expect very tight orbits in this binary driven hypernova model, do you have an expectation of the gravitational wave emission in terms also of the potential observational capabilities today that you can check these scenarios?
I think we have a paper. I think Jorge has a paper dedicated to the gravitational wave of this model.
I see.
It was already mentioned by Jorge this morning, and that is the only reference that we consider of great interest. But let me congratulate Wang Yu also for the presentation, because it helps to give all the numerical value which have been used, the masses, the spin, and all these characteristics which characterize our model, in a summary, to explain also the uniqueness of the role of the different component, namely the supernova event, the mass of the companion neutron star, the mass of the new neutron star, and the spin and all this quantity which makes the system testable. And I think this is very worthwhile, maybe to summarize, while we present with the help of your new slides, when we this case in explaining the relation between the supernova and this observation, and the uniqueness of the supernova luminosity and the time of occurrence. And the same thing should be done for 1901 14C with Raim and co-worker. Lots of new work which is absolutely necessary to explain better the difference of this model from the single object with ultra-relativistic jet. There is no ultra-relativistic jet, and there is not a single object to start with. Many objects and the fundamental role of synchrotron, but not synchrotron in an ultra-relativistic jet, but synchrotron from a spinning new neutron star. These, I think, are the crucial points which we have to emphasize.
Okay, thank you for this comment. We have time for some more questions.
I would like to make a comment, if possible, about this thing. To inform you that with Laura, we actually managed to produce some analytic feeds of the accretion rates, not only on the fallback accretion to the newborn neutron star, but also to the neutron star companion as a function of the orbital periods. I think that will really help a lot in the analysis of the system, because we will very likely manage to make an analytic description of the evolution of both the stars in the first moments. So we are working on that with Laura. So we started with the analytic accretion rates, and from that we are attempting to some analytic description of the new neutron star and the neutron star companion evolution within mass, angular momentum, and the reach of critical mass. So it's coming, I hope, very soon. Thank you.
Good news, very good news.
Very good. Okay, so if there are no more questions, I have a general comment. We expect to have now a huge break until lunch break. And then in the afternoon session, the idea is to start one slot after the 3 p.m., which is supposed to be the first slot for the afternoon session. So we shall start at 3:45 with the talk of Chris Fryer, and then the conclusions of the meeting. So, well, I hope to see you again in the afternoon session. Oh, no, we have a, yes, Jorge's not right hands, but applause. So, okay, thanks a lot to Wonju again, and to all the speakers of this morning session. And yes, see you after lunch break at 3:45.
Thank you.
Bye.